Hey gang, welcome to another worksheet solutions walkthrough. For the worksheet, nailing down NMR terminology and solving problems. Okay gang, so we are pushing into the wonderful world of proton NMR. That's why you're here. Maybe you watched the instructional videos, maybe you gave this worksheet a whirl, and you're looking for some explanations to the answers provided. Well, you are in the right place, my geochemist friends. So we're going to tackle this worksheet head on, do it problem by problem, and hopefully give you the explanations and for the answers you were looking for. Okay gang, so in problem one, all we're tasked with doing at first is looking at these structures and identifying the unique hydrogens. Basically, we need to indicate how many signals we're going to see. Well, how many signals we're going to see in a given proton or NMR spectrum for each structure, okay? So we're playing a symmetry game here, right? So if we look at this first problem right here, and I won't do this for every single one, but I think you can see, I'm just going to fill in all of the hydrogens that we usually leave not drawn. But I hope you're seeing, okay, I see some symmetry right here. I see that these hydrogens are the same as these hydrogens, and I see that these hydrogens are the same as these, and you see that this carbon right here, the carbon doesn't have any hydrogens. So how many signals will we see? We will see two signals, one signal that represents these 6, one signal that represents these 4. So that's how this is going to go. So if we take a gander at the second structure, I hope you're seeing that this is a unique position, 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 right? So we don't have too much symmetry, right? There's no hydrogens here and no hydrogens here because this is a quaternary carbon. And while there are hydrogens, there are also hydrogens at this position as well. And I'm now running out of shapes. But this would be 1, 2, 3, 4, 5. So 5 total unique positions, 5 unique positions, unique areas of hydrogens, if that makes sense. 5 unique hydrogens, you know what I'm saying. And I'll just, I don't know, I'll use an octagon. Oh boy, you know what I mean. These positions are unique. So 1, 2, 3, 4, and 5. We'll have 5 signals for the 5 hydrogens represented in this structure. Okay, so moving on. We see a unique area right here. No hydrogens there. We see a unique position here. There's 1 hydrogen here. So this is a unique position. And then I hope you're seeing that these positions are the same, right? I meant to try and say that over here. These are equivalent. These are symmetrical to themselves. These are the same. So one spectrum will cover these hydrogens, these 6 here. One will cover this 1 hydrogen here. One will carry the 2 here. One will carry the 3 here. So 1, 2, 3, 4. So we will have 4 signals for the NMR spectrum for that structure. So moving down here, I hope what you're seeing is we have what seems to be complete symmetry here. All of these hydrogens are equivalent. So we will have just 1 signal in the spectrum for benzene, okay? Now if we take a look over here, I hope you're identifying the symmetry going along this way. So there are hydrogens here, right? Hydrogen here, no hydrogen there, and we have hydrogens here. So if I'm going to mark equivalent carbons, I'll use a dot here. These are the same, no hydrogens there, hydrogens here, hydrogens there. So we have 1, 2, 3. Oh, and then this position, is wedged in between these groups right here, and there is a hydrogen here. So let me think of, I can circle this. So 1, 2, 3, and 4 signals for that spectrum. And last but not least, I hope you're seeing these positions are the hydrogens here are all equivalent to one another. These 2, right, there's 1 hydrogen here and 1 here. They are equivalent to one another, so we have 2 here. So I did not use my words well here, but you can see that it's all about identifying which hydrogens are, making sure you catch any symmetry, right? And making sure you find the equivalent hydrogens. And it's very common to see problems like this you will obviously get the spectrum problems for sure, and we will get there, right? There's 2 worksheets devoted to doing that, but these are usually some like lead-in problems to NMR questions, identifying how many unique spectrums are for what would be a spectrum given to you, just to make sure you can identify unique hydrogens and things like that. Okay, on to problem 2. Okay, gang, for problem 2, I honestly debated if this was going to be part of the video, but just going to kind of briefly step through. I pretty much just mirrored what the solutions had, and we'll just do a quick run through for each structure, why each position is the splitting pattern was labeled as it was. So if we take a look up here, right, if we take a look at this carbon up here, remember the n+1 rule, neighbors plus 1. So if this carbon we consider 2 neighbors plus 1, that comes to 3. This carbon here has a triplet splitting pattern. So this carbon right here, it has 4 neighbors plus 1, that means 5, a quintet. Same here, this carbon we have 1, 2, 3, 4, plus 1, 5 neighbors, quintet. And then if you ring around the rosy right here, you'll see each carbon, whether it's here, 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 or here, has 2 neighbors, one hydrogen on each. So then plus 1 ends up being 3. So this, and this, all triplets. Moving on to this second structure. I'll start over here. It's beautiful when you see, a carbon with hydrogens and, a carbonyl or a quaternary carbon next door, because that means no neighbors. So N is 0. This is just 1. That's a singlet. Moving on over here. This carbon has, 3 neighbors down here, 1 over here, so that's 4 neighbors plus 1, quintet. If you do the same analysis here, right, 3 on the left, 1 over here, quintet as well. And then over here, 1 neighbor plus 1, 2, doublet, okay? Over here. And again, we're in this scenario, we're assuming the ideal case, right? In actuality, would you have just really messy multiplets? Maybe, but we're not worried about that right now. Over here. So, this carbon, right? 2 neighbors plus 1, triplet. Now this carbon right here with the hydrogens, right? 3, 5 plus 1, 6, that's a sextet, okay? Down here, quaternary carbon next door, so no neighbors there. 2 neighbors over here plus 1, triplet. And then I only showed the hydrogens here because these are all equivalent positions. Their only neighbor would have been this quaternary carbon, which has no hydrogens, so singlet, singlet, singlet. Going down to the second row. We take a look here, right? We see that situation I mentioned before. We have a CH3 and we have no hydrogens next door. This is a singlet. Then, right, no hydrogens, an oxygen. So over here and here, these are equivalent positions. Just 1 neighbor, so that's a doublet, right? 1 plus 1. And then this hydrogen right here has 6, 6, and then 1, so 6 plus 1, 7. That's a septet, okay? S-E-P-T-E-T. Okay, over here. Don't forget about oxygen or hydrogens on alcohols. They count too. So, right, singlet. No one, its neighbor right here has no hydrogens to split with. Over here, right, we have, this bond right here occupies the position where hydrogen can be. Ditto over here, so singlet for that hydrogen. Down here, right, no neighbors up top, just 1 neighbor over here. So 1 plus 1, that's 2, a doublet. Over here, right, neighbor to the left, neighbor to the right, 2 plus 1, triplet. Over here, no neighbor up top, 1 neighbor over here, 1 plus 1, doublet. Over here, so I expanded what was the ethyl group, right? So on the actual structure you had, so this was the ring, you had this, so, oh whoops, not that, you had this. So I expanded that, so when you have this, right, no hydrogens here, so right here you just have 3 over here plus 1, that's a quartet, 4. And then over here, you consider the 2 neighbors here plus 1, that's a triplet. Then over here, we see the singlet up top. Down here, no neighbors here, 1 neighbor to the left, that's a doublet. Over here, no neighbor up top, but 2 and 2 plus 1, that's a quintet, because that's 5. Over here, right, we have 1 neighbor, that's 1. 2 over here, that's 3 plus 1, that's a quartet. Down here, we see 2 neighbors, so 4 plus 1, that's a quintet as well. So these 2 are quintets. Down here, no neighbors to the right, 2 neighbors to the left, 2 plus 1, triplet. Okay, gang, that does it for 2. On to 3. Okay, gang, so in the first part of problem 3, we have to identify which of the following structures has 1 signal in its HNMR or proton NMR spectrum. So if we take a look here, right, this is a problem dealing with symmetry. So we know, if you look back at the first page of the worksheet, we've already seen this before, and we know that these positions, this is 1, and this is 1. So this already has 2, so that's a no-go. I hope you can see that all of these right here are equivalent. And there's one hydrogen here, 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 and here, all equivalent, so I'll put little squares around them. So again, we're going to see 2 signals. So 2 signals and 2 signals. If we take a look here, equivalent, 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 equivalent. And I know let me fill these in because we have oxygens in the ring. This is our structure that has 1, and just to be sure, looking over here, these positions are equivalent. There's no hydrogen. There's no hydrogen at this position right here because 1, 2, 3, and 4. 1, 2, 3, and 4. But there are hydrogens here, 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 and here, and they are all equivalent. So I can put squares around here. This has 2 signals as well. So long story short, beating the explanation dead. This is our structure that has 1 signal in its H-NMR spectrum. So on to the second part of problem 3. In part 2 of problem 3 of the 4 structures given, we need to identify which structure has both a singlet splitting pattern signal and a signal with a chemical shift of roughly 4.1. So I think hopefully these are starting to get a little bit more apparent to you. You have some hydrogens that really have no neighbors, right? And that's very typically seen when you have an ether, right? So like you have a terminal, maybe CH3 with an oxygen, right? So when it's part of the chain, there's no neighbors, or you have a carbonyl, carbonyl like a ketone, or you have, and what's the last? Oh, a quaternary carbon. So maybe you have like a T-butyl group, and that carbon next door won't have any hydrogens, right? Okay, so if we take a look right here, the first thing I'm going to personally look for is that the verbiage on the worksheet could have probably been better. These are 2 different chemical shifts because chemical shift of 4.1 is very indicative of an alcohol, and those are always singlets. So these are 2 different singlets. 2 different. Okay, cool. So if I'm looking over here, I do see they all have an alcohol, right? Alcohol, 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 alcohol. So that works. So I don't see the singlet, the carbon, singlet there. There's, there will obviously the alcohol is taken care of, but this will be, so 2, 2, 1, that's quintet. 1, 2, that's a quartet, and a quartet as well. So here, right, we have the alcohol. There's going to be a singlet that represents both of these 2 hydrogens, but we don't see any singlets there. Here, we don't see any singlets as well, but I hope you're seeing, here is that CH3 that has no neighbors right here. So this is our singlet. Here is the chemical shift of roughly 4.1 right here in the alcohol. Whoa, butterfingers, there we go. So it's this right here, draw a big circle. Be happy because that is the answer to the second part of problem 3. So let's round this out with the third part and that little bonus question. Okay gang, to round out this worksheet, we're going to tackle part 3 of question 3 and the bonus question. Okay, so if we take a gander at the 4 structures given here, we need to identify the 1 or 1s, right, that have 2 units of unsaturation and 4 unique signals on their respective proton or H-NMR spectrums, okay, or spectra. So if we take a gander here, let's go left to right. So I hope you can see, right, remember units of unsaturation, those are rings or double bonds because when you add them, you have 2 less hydrogens, right? If you add 1 of whatever, you lose 2 hydrogens, right? It creates an unsaturation, a unit of unsaturation. Okay, so we take a look here, right? If we just do all 4 real quick. Ring, double bond, 2 units of unsaturation. Ring, double bond, 2 units of unsaturation. Double bond, 2 units of unsaturation. Ring, double bond, 2 units of unsaturation. So we have this condition satisfied everywhere. So let's see what kind of signal count we get from each structure. So on this structure right here, this is a unique position, right? There's no hydrogens here, that's why I skipped it. This is a unique position, unique position, unique position. So we have a match here. This is good to go. This fits our criteria. So let's keep going. So no symmetry here. We have a signal here, a signal here, a signal here, a signal here, a signal here. So we have 5 signals. Unfortunately, it does not make the cut. Now, if we go over here, we see hydrogen here, a little weird because it's on it's on a carbon that has a unit of unsaturation. So we have an aldehyde. So 1, 2, 3, 4, and 5 because we have no symmetry. So 5 signals. Put an X right there. And then last but not least, I hope you can see no hydrogens here. We have unique, symmetrical positions right there. That's 1 signal. Then we have a second, and then we have a third. So that's 3. Doesn't make the cut. So it was our first structure all along. Okay, and so for the bonus question, we need a structure that has 1 signal in its its proton NMR spectrum. It needs to have at least 6 carbons, and it needs 4 units of unsaturation. I threw this in just to reinforce this, tuck this in the back of your mind. When you do a problem that has 4 units of unsaturation, or this will typically come when you do more NMR problems, NMR problems. If you lean on your good old friend benzene, what you will see is symmetry, 1 signal, right? That will represent all of the protons in the structure, as well as 1, 2, 3, and 4. 4 units of unsaturation. Benzene is the easiest, simplest example you can come up with here. Okay, gang. Thank you so much for rocking with me on this NMR worksheet. I hope if you were looking for some explanations to the answers provided, you got them. If you're watching this video, that means you financially supported jOeCHEM, and I can't thank you enough. I'm so humbled you're using the website at all. I hope it is propelling you to success in your organic chemistry class. I hope it's everything you were hoping to get out of it, and I'm glad you're using it now, and I hope you're using it to the very end of your organic chemistry days. But if anything, I hope to see you all in the next video.